this episode, we're going to make transport layer security, TLS, failures feel predictable instead of mysterious. Beginners often experience TLS problems as random moments when a website won't load, an app shows a scary warning, or a connection suddenly becomes slower or less reliable. It's tempting to treat those moments as mere technical glitches, but in security, those failures are often the system telling you something important about trust, identity, or negotiation. Sometimes the warning is a real signal that an attacker might be trying to intercept traffic, and other times it's a sign of misconfiguration, outdated settings, or expired credentials. The key is learning how to interpret the most common failure patterns: downgrades that push connections into weaker modes, certificate errors that break the identity promise, and trust breaks where the chain of validation fails. We'll also touch on why Secure Sockets Layer, SSL, still comes up in conversation even though modern secure connections use TLS. By the end, you should be able to hear about a TLS problem and immediately think, which part of the security contract failed, and what does that mean for risk? It helps to begin with a clear mental model of what TLS is supposed to do when it is working. TLS is a protocol that protects data in transit between a client, like a browser, and a server, like a website. Its job is to provide confidentiality so eavesdroppers can't read the traffic, integrity so attackers can't change the traffic without detection, and authentication so the client can be confident it's talking to the intended server identity. Those goals depend on a negotiation step, often called a handshake, where the two sides agree on protocol version and cryptographic settings, and where the server proves identity using a certificate. If all of that succeeds, the connection becomes a protected channel. When TLS fails, it usually fails in one of those phases. Negotiation can fail or be manipulated, identity validation can fail, or the channel can be disrupted by devices that can't handle modern security settings. Thinking in phases makes failures easier to interpret because you can ask, did the parties fail to agree on safe settings, or did the client refuse to trust the server's identity? Now let's address why SSL is still mentioned, because the terminology can confuse beginners. SSL refers to older protocol versions that are no longer considered safe, but the name stuck in everyday language, so people still say SSL when they mean TLS. That habit isn't just a vocabulary issue. It can hide real risk when systems still support old versions for compatibility. A site might claim it supports SSL as a selling point for older clients, but that can mean it is willing to negotiate unsafe options. Modern secure design treats older protocol versions as deprecated and disables them, because attackers can exploit weaknesses or force a downgrade to those weaker versions. So when you hear SSL in a technical discussion, one useful beginner reaction is to ask whether someone is using the term casually or whether an old protocol is actually enabled. If an old protocol is enabled, that is a clue that downgrade risks and compatibility misconfigurations may exist. Downgrade failures are a major category of TLS problems, and they stem from the fact that many secure connections involve negotiation. Negotiation means the client and server try to find a shared set of options they both support, like versions and algorithms. Attackers can sometimes exploit that by interfering with the negotiation so the connection falls back to weaker settings, either by making strong options appear unavailable or by nudging the client into using an older version that has known weaknesses. Even without an attacker, misconfiguration can cause downgrade behavior if a server is set up to prefer older options, or if a client is outdated and cannot use modern options, forcing a lowest common denominator result. The dangerous part is that a downgraded connection can still appear encrypted, which can give users false confidence. That's why modern designs try to remove weak options entirely, so there is no safe-looking but weak state to fall back into. A good security posture is often fail-closed, meaning if safe settings can't be negotiated, the connection should fail rather than quietly becoming weaker. Certificate errors are another common failure type, and they are often the most visible to users because browsers show warnings. A certificate is the server's identity credential, and when the client validates it, it's checking that the certificate is currently valid, issued by a trusted chain, and matches the identity the client intended to reach. One common error is expiration, where the certificate is outside its valid date range. That might sound like harmless paperwork, But it matters because expiration is one of the ecosystem's ways to limit risk over time, and ignoring expiration trains users to ignore trust signals. Another common error is name mismatch, where the certificate's identity doesn't match the site the user is visiting. That can indicate misconfiguration, but it can also indicate interception or redirection to a different endpoint. There are also errors where the issuer is not trusted, meaning the chain does not lead to a trusted route in the client's trust store. Each of these errors is the client saying, "I cannot prove this server is who it claims to be," so proceeding may expose you to impersonation. Trust breaks often show up as chain validation failures, and those failures can be surprisingly subtle. The server's certificate is rarely signed directly by a widely trusted root. Instead, it is signed by an intermediate certificate, which is in turn signed by a root. The client needs the chain to validate all the way to a trusted root, and it also needs to ensure each certificate in the chain is allowed to play its role. A trust break can occur if the server fails to provide the needed intermediate, if the intermediate is missing from the client's ability to build the chain, or if the chain violates policy constraints. It can also occur if the root or intermediate has been removed from trust stores due to compromise or misbehavior. For beginners, the key idea is that trust is a layered endorsement system, and if any endorsement is missing or disallowed, the client will refuse to treat the identity as proven. In the real world, that can look like a sudden wave of outages when a widely used intermediate changes status, even if the end certificates themselves haven't changed. Revocation-related behavior can also create confusing TLS failures, even though revocation checking is often imperfect. Revocation is supposed to allow clients to reject certificates that should no longer be trusted before they expire, such as after key compromise. But clients may not always be able to check revocation status reliably, and different platforms make different choices about what to do if the check can't be completed. Sometimes a client might proceed anyway to avoid blocking users due to transient network problems, and other times a client might treat revocation status as essential and refuse the connection. This variability leads to situations where a connection works on one device and fails on another, even though they are both doing TLS. The important beginner lesson is that revocation is not always a crisp on or off gate in practice, and you should treat revocation as one signal among several, not as a guarantee that bad certificates will always be blocked. When a system does enforce revocation strictly, failures can show up as sudden trust breaks that feel unexpected unless you understand the revocation ecosystem. Another common source of failure is interception devices that sit between clients and servers, often for monitoring or filtering. In some environments, network security tools act as a middle point that inspects encrypted traffic by establishing a secure connection with the client and a separate secure connection to the server. For that to work without constant warnings, the environment must install a trusted route for the interception system on the client devices, so the client treats the middle device's certificates as valid. When this is misconfigured, users see certificate errors because the client cannot validate the presented identity chain. Even when it is configured, it shifts trust because the client is now trusting the interception system to handle encryption and identity correctly. This can create new failure modes, like breakage when the interception system can't support modern settings or when it mishandles certificate validation. The beginner takeaway is not that interception is always bad or always good, but that it changes the trust model and can create both security and reliability consequences. Time-related issues are another surprisingly common source of certificate problems because certificate validation depends on accurate clocks. If a device's clock is wrong, it can think a certificate is not yet valid or already expired, even when the server is configured correctly. That can happen with misconfigured system time, disabled time synchronization, or unusual environments where devices can't reach time sources. For beginners, this can be confusing because it looks like a security error even though the server certificate is fine. But conceptually, it makes sense because the validation rules rely on time to enforce certificate lifetimes. This is a great example of how security depends on supporting infrastructure beyond cryptographic math. When time is wrong, trust decisions become unreliable, and the system errs on the side of caution by refusing to trust what it cannot validate properly. One of the most important mindset shifts is learning to treat TLS failures as a form of protective friction rather than as pure inconvenience. When a browser warns you, it is usually telling you the server's identity cannot be proven under the rules that normally prevent impersonation. When a connection fails after a configuration change, it may mean the server is offering only weak options, or the client is too outdated to support modern safe settings. When systems negotiate down to older modes, it may indicate a compatibility choice that widened the attack surface. In each case, the failure is pointing to a specific kind of broken promise: identity, negotiation safety, or trust chain integrity. If you ignore the failure without understanding it, you may restore functionality at the cost of opening a real security gap. If you interpret the failure correctly, you can fix the underlying issue while keeping the security contract intact. That is the difference between keeping TLS as a protection mechanism and turning it into a checkbox. To wrap up, TLS failures generally fall into a few predictable categories: downgrades that push a connection into weaker or unsafe settings, certificate errors that prevent identity from being validated, and trust breaks where the certificate chain cannot be built to a trusted root or violates policy rules. The continued use of the term SSL can hide risk when older protocols are still enabled, and negotiation-based designs can be exploited if weak options remain available. Certificate warnings are not just noise. They are signals that the identity proof failed, and proceeding may expose you to interception or impersonation. Revocation and interception add complexity, sometimes creating inconsistent behavior across devices, while simple infrastructure issues like incorrect time can cause validation to fail. If you keep the handshake phases in mind and ask which promise failed, you can interpret these problems without panic and without dismissing them as harmless. That ability to reason about failure modes is one of the most practical security skills you can develop because it helps you preserve secure communication when it matters most.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.